I think the recording is in progress. Well, Jacob, I really appreciated the introduction, talking to all of the people beforehand. That was wonderful. It gave me a sense that this audience knows at least some bit about QBism, and it won't come as a surprise to many of you that, oh, I have to hit something before I can go on. It won't come as a surprise to many of you that QBism has had a rather contentious relationship with a number of philosophers. I thought I would kind of summarize the interchange to get things started. My experience of how most philosophers of physics engage with QBism is, wah, 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 you're not realist enough for us. The way we QBists think instead is it is the world that decides which philosophy best fits it, not the other way around. We took a gamble 20 years ago that an epistemic view of quantum states was the best road to progress and followed its consequences. We figured nature, not philosophers, would let us know if we were or were not on the right track. So we busied ourselves doing what we do, building a consistent picture, proving theorems, methodically dissecting the theory. It has been a long, hard road. It wasn't born in a scallop shell, as Venus was. But instrumentalism or anti-realism was never a presupposition. QBism has always been a methodology for unearthing an ontology. QBism has always been a methodology for unearthing an ontology. Basically, QBism is a project, and I thought what I might do with this talk is give some of the history of how we've seen QBism develop and what we think it has addressed, and in the latter half of the talk about what I view as some of QBism's structural statements, something akin to a kind of structural realism, probably in a way that won't satisfy most people, but again, QBism is a project, and so the idea is to look for hints where one can. And then I believe in Jacques Pinard's talk, he'll talk about the ontological project from a more phenomenal point of view, or phenomenological point of view. The guidance toward QBism started in the early 1990s when I came under the influence of Carlton Caves, who was already under the influence of E.T. James. And I first came across one of his articles from the 80s where he said, our present quantum mechanical formalism is a peculiar mixture describing in part laws of nature and in part incomplete human information about nature, all scrambled up together by Heisenberg and Bohr into an omelet that no one has seen how to unscramble. Yet we think the unscrambling is a prerequisite for any further advance in basic physical theory. When I first saw that, it hit me in the head like a brick, because for the first time I started to appreciate that perhaps a lot of the foundational difficulties or interpretational difficulties were precisely this, that quantum mechanics was a rather ill-defined mixture of both epistemic and ontic elements, and he was really on the right track, that we need to unscramble the omelet before we can hope to say something meaningful about an ontology. If, for instance, you think of a wave function as information, and yet you try to ontologize it, maybe you're creating a lot of trouble for yourself. So the beginning point of the effort for QBism was to recognize, like every physicist recognizes, that the world is made of some stuff. And it's the task of physics to try to say as much as it can about the character of the stuff. Say as much as it can about what is out there in the world. On the other hand, when we practice quantum mechanics, we start with this mathematical symbol, the quantum state. And the main thing that I'd like to address in this talk is the question of, well, what is the relation between these two things? These are two things. One is what the world is made of. The other is the symbol that appears in one of our theories. What's the relation? QBism decided early on, as I said, that quantum states fall somewhere in this spectrum. Somewhere in the spectrum of information or knowledge, in other words, an epistemic notion, or belief, a doxastic notion, that's a word Chris Timpson taught me, or simply pragmatic gambling commitments. I don't know if I would call that maybe the opportunistic formulation of quantum states. So early on, we decided that it's somewhere in the spectrum there, and it's been a large part of the research effort since then to try to figure out where exactly in the spectrum it is. One of the reasons for the move in the early 90s was that it had an immediate explanatory power. And this, I don't take this very lightly, immediate explanatory power for explaining a number of phenomena in quantum information and showing that the roots of the phenomena are basically the same, namely in some kind of epistemic character for quantum states. Let me just give as one example the quantum no cloning theorem. You know that there's no physical process that will take psi to 2 copies of psi unless the device already knows the identity of psi. Scott Aronson in one of his blogs says, the subject of this talk is a deep theorem that stands as one of the crowning achievements of our field. I refer to the no cloning theorem. I'd like to pose the question, why should our universe be governed by physical laws that make the no cloning theorem true? Well, from the point of view of QBism, it's hardly one of the crowning achievements of the field. Classically, the epistemic states, the Liouville distributions on a phase space, can't be cloned either. That's a corollary of Liouville's theorem that we first appreciated, I think, in 1994. It was only the prejudice that quantum states should be thought of ontically that made the no cloning theorem look like a big deal. So that's one example where we felt that we had immediate explanatory power for this. I could tell you a similar story for quantum teleportation and quite a number of other phenomena in quantum information. But maybe there are tougher questions. Maybe if I move out of the purview of quantum information, maybe there's some things that taking this point of view does an injustice for. Here's one example of a potentially tougher question. It's something that one sees or hears in nearly every philosophy of physics meeting, something that Tim Maudlin put very nicely. What Bell proved, and what theoretical physics has not yet properly absorbed, is that the physical world itself is non-local. What Bell proved, and what theoretical physics has not yet properly absorbed, is that the physical world is non-local. We poor physicists, we haven't yet properly absorbed it. Well, it makes us suspicious because we find ourselves, at least physicists, not so much philosophers of science, we find ourselves asking, well, if there's non-locality, where does it stop? What makes the experiment in my laboratory meaningful when someone across the universe could sneeze and the outcome of my spin measurement be changed as a consequence of it? Well, because of considering problems like this, QBism found itself, if it was, maybe I shouldn't even call it QBism because it was so nascent at the time, it was initially quantum Bayesianism. Or first it was the Bayesian approach to quantum states, but we found ourselves in answering various of these questions going down this spectrum, going down the hierarchy, finding ourselves pushed into a corner of more and more subjectivist notions of quantum probabilities. This is one example of a question that led in that direction, and I think rather fruitfully. Where we ended up with is the notion of probability of Bruno Definetti, which Dennis Lindley put very nicely. He called it the Coherentist paradigm. The topic studied is the situation of an individual who is faced with uncertainty about some events of concern to him. All of us find ourselves in this position. So he takes the uncertainty in the world as a given. All of us find ourselves in this position. Definetti's task is first to recognize openly the uncertainty surrounding us and then see how we can best understand it. The main result is that uncertainty can only be described satisfactorily in terms of probability. The coherentist paradigm is egocentric. It is a tale of a single person contemplating the world and not wanting to be stupid. He realizes that to do this, his statements of uncertainties must satisfy the laws of probability. So the key idea here is that probability theory is set up so that we avoid stupidity. How can you put this in play or put it in action? Well, you take Diffinetti's notion of probability. So the very meaning of probability, according to Diffinetti, is defined by how one would be willing to gamble. When a bookie declares PE, P sub E, for an event E, what he means is that one will buy or sell a lottery ticket that's worth $1 if the event E occurs for P sub E dollars. So in other words, if you're willing to buy or sell tickets at this rate, then that is a quantification of your probability assignment. Now, that is a really unstructured notion. Probability theory has all kinds of rules. There's the additivity law, there's Bayes' rule, and so forth. And it's hard to see how one could take such a thin notion of probability and get such a thin notion of a definition of probability and get the actual structure of probability theory. But Diffinetti noticed that if you add one further ingredient, a normative rule, the normative rule that a bookie should never declare probabilities that will lead him or her to a sure loss. Just imposing this rule is enough to derive the full probability calculus. So this is not a frequentist notion. You don't have to talk about many copies of the event E or not E or so forth. It's just simply if these are his gambling commitments for the various lottery tickets, unless these laws are satisfied, then one can buy and sell some tickets to the bookie such that he will definitely have a sure loss. So you get the additivity law, you get Bayes' rule, etc. So this gives us a normative reading of probability. Just consider this case for the law of additivity. It could be, or I should say this, that it's easy enough to write down probabilities and do textbook problems. But in the real world, one has all kinds of considerations that must go into their probability assignments. For instance, maybe the tools of reasoning that lead an agent to this probability assignment for E or F comes from one source of thinking. But perhaps the probability assignment for E comes from a completely different source of thinking. This one comes from reading the Washington Post. This one is aided by reading the New York Times. And this one is aided by reading Fox News, perhaps. What the normative reading of probability theory says is when an agent makes these assignments, if they don't fit together according to this equation, then something is astray and the agent has exposed himself to a sure loss. So if the equation's not satisfied, the agent should rethink his various assignments and adjust them so that the law of total, or the law, additivity law here, is satisfied. So this is what I mean by normative reading. Now I'm going to aim to put quantum theory in terms of a normative reading in a little bit, but I want to give this as the first introduction. From this point of view, what means certainty? What means probability 1? Well, if you take the coherentist paradigm seriously, then you can say the only thing probability 1 can mean is that an agent is willing to buy or sell a lottery ticket that's worth $1 if E, for in fact $1, full stop. That's all it means. Particularly, probability 1 does not imply the truth of a proposition or the existence of a physical fact from this point of view. It just means that if the agent is being as coherent as possible with all of his various other probability assignments, And if coherence then requires probability 1 for some particular proposition, then this is what he should be willing to buy or sell a lottery ticket for. Richard Jeffrey said it very nicely. Jeffrey said, the Bayesian framework replaces affirmation and denial by a continuum of judgmental probabilities in the interval 0 to 1, endpoints included. 0 and 1 are probabilities no less than 1/2 and 99/100ths are. Probability 1 corresponds to infinite odds, 1 to 0. That's a reason for thinking in terms of odds, to remember how momentous it may be to assign probability 1 to a hypothesis. It means you would stake your all on it, but it doesn't mean that the proposition or the event is true. So let me show one application of this idea. Everybody knows the EPR criterion of reality here. If without in any way disturbing a system, we can predict with certainty, i.e. with probability equal to unity, the value of a physical quantity, then there exists an element of reality corresponding to that quantity. If we can predict with certainty, then there exists a value. Tim Maudlin says, if I could make one change to the EPR paper in retrospect, it would be to alter the characterization of this criterion. The authors call it reasonable and in agreement with classical as well as quantum mechanical ideas of reality, but its status is actually much stronger than that. The criterion is, in the parlance of philosophers, analytic. That is, this criterion follows just from the very meanings of the words used in it. Well, not in QBism, for the very reason that the words in it aren't used in the same way that Tim Maudlin is using them. That, in fact, is enough to get rid of tickle, tickle, tickle with some further argumentations. So the point of going down this spectrum of information, knowledge, belief, pragmatic commitment is that in traveling down that route, we found that we could solve more and more so-called foundational conundrums. But all the while, and I have to emphasize this over and over and over because people like my good friend Czesław Bruckner don't listen, all the while, this was done, despite the appearance of it, in a pursuit of finding an ontology for quantum theory. So let's tighten up this conception just a little bit more. Yeah, but a quantum state is not a probability. It's something more than that, right? Why? Well, look at what we do with quantum states. We calculate probabilities from them. If just looking at this, we know that a quantum state is always given first, and then a probability is calculated second. From the view of this diagram, the quantum state is logically prior to a probability. So it may be that these probabilities are all subjective, but they arise from this deeper notion, the quantum state. But in fact, if you know enough quantum information theory, you know that you can reverse the order. By considering a robust enough set of measurements, you can completely specify a quantum state. So if you have a robust enough set of measurements and you look at their probabilities, you can completely specify a quantum state. Since we QBists are committed to the coherentist paradigm for understanding probabilities, the lesson we draw from this is that this entity must have to do with a tale of a single person not wanting to be stupid. And this is where our effort needs to be pushed to understand this. In what ways is one being stupid if one doesn't follow the quantum formalism? So here's, in a nutshell, the worldview of QBism. I'm sorry it's a long quote, but I think it does it so perfectly that it's worthwhile. This is a description of a term that the US Judge Oliver Wendell Holmes made up, and it comes from Louis Menand's really marvelous book, The Metaphysical Club, which is a kind of history of early American pragmatism. Menand writes, "The loss of certainty is a phrase intellectual historians have used to characterize the period in which Holmes lived. But the phrase has it backward. The loss of certainty has it backward. It was not the loss of certainty that stimulated the late 19th century thinkers with whom Holmes associated. It was the discovery of uncertainty. Holmes was, in many respects, a materialist. He believed, as he put it, that the law of the grub is also the law for man. The grub is a little worm. So there's nothing special about us in Holmes's view. He was not a determinist because he did not think that the course of human events was fixed. Complete certainty was an illusion, of that he was certain. There were only greater and lesser degrees of certainty, and that was enough. It was in fact better than enough, for although we always want to reduce the degree of uncertainty in our lives, we never want it to disappear entirely, since uncertainty is what puts the play in the joints. Imprecision, the sportiveness, as it were, of the quantum, is what makes life interesting and change possible. Holmes liked to call himself a variabilitarian. We cannot know what consequences the universe will attach to our choices, but we can bet on them, and we do it every day. We make a gamble, a bet, every time we cross a busy street. We're constantly gambling. We may not be quantifying it in terms of probability theory, but this is the life that we have because we're in a world where there is uncertainty for whatever reason. Uncertainty may come from ignorance, but uncertainty may come from downright indeterminism in the world, as quantum theory, I would say, seems to show us. So from our point of view, here we are, we're in this uncertain world, and we have to make decisions all the time. QBism views quantum theory as an addition to decision theory. In other words, the discovery of quantum theory made us better variabilitarians. QBism means quantum variabilitarianism. Now, many philosophers will want to say, pah, that's just instrumentalism. That's just anti-realism. And being an instrumentalist is a bad thing, right? Because then your theory tells you nothing whatsoever about the world, or at least that's the usual conception. But I want to differ with that. I want to differ with that in the following way. Fine, yes, QBism will take the calculus of quantum mechanics as an instrument. But it does it, let's say, in the same way as this little single-celled organism, the euglena, takes its tail. The tail is there for the purpose of wiggling the little euglena from some area in its environment where there's maybe not a great nutritious value. He feels the gradient of the nutrients and wiggles over here so that there's more things available for him. In that way, the tail is like quantum theory. It's an instrument that's used by this little agent. But just because it's an instrument doesn't mean that it cannot be studied. For instance, one might take the tail and meticulously take a cross-section of it and notice whether the tail is round or whether it's elliptical in cross-section or whatever the characteristics are. Implicitly, that tells us something about the sort of fluid that the euglena is swimming around in. One might study the ratio of the width of the tail to the length of the tail, and implicitly that tells us something further about the environment. So even declaring that quantum theory is a tool, is an instrument for making better decisions, doesn't mean that one might not squeeze something out of it about the character of the world. And now for QBism as a project, the only question is, what's the best way to go forward in that task? How can we study the instrument and from it try to learn something about the character of the world? This leads me to the technical side of QBism. that I sort of feel that people need to know that QBism is a living subject with lots of mathematical theorems and consequences. So Jaynes, in an appendix to what I'd read earlier, said, of course, the quantum mechanical formalism also contains fundamentally important and correct ontological elements. It seems that to unscramble the epistemological probability statements from the ontological elements, we need to find a different formalism, isomorphic in some sense, but based on different variables. It was only through some weird mathematical accident that it was possible to find a variable psi which scrambles them up in the present way. So the technical side of QBism for the last probably 10 years has been devoted to trying to find a different formalism for quantum theory, one that can reveal something about this thing that we're aiming to get at. Here we take guidance from a 1951 paper by Richard Feynman titled The Concept of Probability in Quantum Mechanics. Feynman writes, the new theory asserts that there are experiments for which the exact outcome is fundamentally unpredictable, and that in these cases, one has to be satisfied with computing probabilities of various outcomes. But far more fundamental than the unpredictability, far more fundamental was the discovery that in nature, the laws of combining probabilities were not those of the classical probability theory of Laplace. What is changed, and changed radically, is the method of calculating probabilities. Now, Feynman, of course, had in mind the double slit experiment. And you all know from his 1964 lectures, he said, we choose to examine a phenomenon which has in it the heart of quantum mechanics. In reality, it contains the only mystery. Here's the way I like to think of the double slit experiment. The double slit experiment is not one experiment, it's 3 experiments. So one possible experiment is that the electron gun fires and the particles, quote unquote, go through the slits, and then we see the probability distribution of where they land on the backstop, and we find this distribution. That is one experiment. Another possible experiment is that we block one of the detectors and find the probability distribution that lands on the backdrop, or we block the other detectors. Or as Feynman argues in his paper, we didn't even have to block the detectors. What we could do is put extra detectors at the slits and see which slits the particles went through, and that's enough to erase the interference pattern. So maybe I shouldn't say 3 experiments. Let me think of 2 potential experiments. One is without detectors at the slits, and one is with detectors at the slits. And then what Feynman argues, of course, is that this P12 is not the sum of P1 plus P2. Something changes, the laws of combining probabilities changes, and the way it does is by introducing amplitudes. And now, in fact, we can make a connection between this probability distribution and these probability distributions through these amplitudes. So I think that's the essential thing that he was trying to get at back here when he said, far more fundamental was the discovery that the laws of nature of combining probabilities were not those of the classical probability theory. But what he was talking about were amplitudes. And it looks like an extra ingredient above and beyond the probabilities enters the story. And I think by introducing complex amplitudes, it really distracts from the seminal point he made in 1951. And besides, this is open to the criticism that it is just one experiment after all. And there are many kinds of experiments that one can have in quantum theory. So what I'm going to aim to do with my last 12 minutes is generalize Feynman so that, in fact, it does capture every experiment that can be done in quantum theory. And what I mean by that is every experiment where one uses the Born rule, and it also captures unitary time evolution, though I'm not really going to talk about that part of it today. So I want to generalize it in a way that it captures every experiment that can be done, in the sense of experiments for which we use the Born rule to calculate probabilities. And I want to do it in a way that doesn't introduce complex amplitudes, so that I can compare it directly to the laws of probability theory in a way that Feynman couldn't. So let me introduce to you the idea of the d-squared non-orthogonal slits experiment. In this experiment, here's basically what we have. We have a quantum system prepared in some quantum state. We're going to send it through something I'll call a reference measurement. That's why the R is chosen for the symbol. So the quantum system goes through a reference measurement, comes out in a new quantum state, sigma I, and then proceeds on to some other experiment. You'll notice the analogy here. This is like the backstop. This experiment here is like the backstop in Feynman's double slit experiment. And this experiment here, when it is flipped to the on position, is like putting detectors at the slits. And when it is in the off position, it's like turning off the detectors at the slits. I'm going to consider this in the setting of a finite dimensional Hilbert space of some dimension d. So there's this d squared is important because d squared refers to the dimensionality of the Hilbert space. So just to reiterate, we send a quantum system in some quantum state through a reference measurement. There is a click, some value of Ri is chosen, and it occurs with some probability P of Ri. Then the quantum system comes out in a new quantum state, sigma I, that directly depends upon which click was gotten here. And then it travels to a further quantum measurement that I'll call E. E for effect, R for reference, E for effect. Now I've got to do something based on using quantum information theory here. The measurement in the middle can't be just any quantum measurement. It has to be something called an informationally complete quantum measurement. And for specificity, I'm going to make it a minimal informationally complete. That means it has d squared outcomes. The measurement over here, on the other hand, can be any quantum measurement whatsoever. It need not be fixed. So there's the reference measurement, a very special one that we're going to choose for all time's sake and never change it. It's kind of like choosing a coordinate system on a manifold. And then we will allow these other measurements to vary. So consider this. Imagine the switch is turned on, but I go to my diagram and I erase the quantum state rho here. I erase the operators R sub I here, and the operator sigma I here, and these operators here. The only thing I leave behind in my diagram are the probabilities, P of Ri, P of Ej given Ri, and P of Ej. So here, this is, I've taken away the quantum state here, I've taken away the quantum state there. I've just called this a variable R. I'm not calling it by name in terms of operators anymore. And there's some probabilities for the outcomes, P of Ri, P of Ej given Ri, and the overall P of Ej. Nothing to do with quantum mechanics. We know how these probabilities have to fit together. They have to fit together according to the law of total probability, else an agent would be incoherent. He could be taken to the cleaners by an adversary, a gambling adversary. So even in the quantum mechanical case, as long as this switch is on, we would use the classical law of total probability. And I'm going to write this in a vector notation so that it just kind of makes it easier to understand. This is a vector P of E. It's a vector of numbers. P of E given R is a matrix, stochastic matrix, and P of R. This is it in component form. This is it in vector form. In personalist Bayesianism, the law of total probability is normative guidance. It doesn't tell an agent which probabilities to use, only how they should fit together. Contrast this, what we've just talked about here, with the situation of when I turn the switch off. If I turn the switch off, then what we've got is a quantum state going in, there's nothing here, quantum state continues on, and goes to this measuring device. Now I can't forget about the fact that this is an operator and these others are operators over here. I can't forget about that at all because they're necessary for calculating my probabilities. Now it's not the law of total probability that is our normative guidance. It is the Born rule. So the Born rule just says, take the Hilbert-Schmidt inner product of the two operators, and that calculates the probabilities. What I'd like to know is, can we do better? Can we make it clear that this too is normative guidance, much like the law of total probability, but conditioned on the character of the world we are immersed in? Well, a rather simple manipulation can recast the Born rule. In other words, we can recast this equation, interestingly, in terms of the probabilities that appeared over here. So we do that. And this is what we get. We get that the Born rule probabilities on the left are calculated from the other probabilities that occurred in the experiment where the reference measurement was on, when the reference measurement was on. But it's not exactly the law of total probability. There's an extra matrix here, phi, whose inverse is defined in terms of the reference measurement alone. And so now we notice something. The sole difference between classical and quantum normative guidance, in this way of putting it, resides in the fact that phi is not the identity matrix. So if phi were the identity matrix, this would be the law of total probability. But in fact, you can prove a theorem that says that for no reference measurement here, or back here, for no reference measurement whatsoever, can the phi matrix ever be the identity. So there's the difference between the two different experiments. So we're left with a picture of Feynman made general and without amplitudes. It says that the Born rule tells us something about connecting one experiment to another through the probabilities. The probabilities are related to each other. There was no reason that they had to be related to each other. This is a point that's been brought up by Leslie Ballantyne and Koopman. I can't remember Koopman's original name, his first name, when they had their disagreement with Feynman. They said there are extra conditions here. These are differing experiments. And that is true. But what's important and what's interesting is that quantum theory gives the glue for connecting the probabilities in the different situations. So we end up with this. Like the law of total probability, the Born rule is a normative relation between probabilities. Now even Bruno De Finetti can make sense of what quantum theory is about. Quantum theory is not about objective probabilities. Instead, it is about extra normative glue for one's probability assignments. But what about the new formalism? How are we going to find that new formalism that I've really been seeking? Well, I've already shown you part of it. Part of the new formalism is there's the Born rule, written without any quantum states. There are no wave functions. There are no complex probability amplitudes. Everything is a real number. Everywhere in the equation, there are only real numbers. So there's part of the formalism. But have we squeezed everything from it that we can? And I think, no, we haven't yet. What we now have is an opportunity to explore, okay, this isn't the law of total probability, but depending upon the phi, it can come closer or further away. If we really want to know the distinction between classical thinking and quantum thinking, we should try to find how close the matrix phi can be to the identity. In that way, we can identify an irreducible difference between quantum theory as a normative theory and classical probability theory as a normative theory. So you can pose the question, what is the irreducible quantumness? So what I mean by the irreducible quantumness is that it's defined by the phi, for any finite dimensional Hilbert space, such that the distance between the identity and phi is minimized. Well, it might depend upon which norm we use here, but in fact, it doesn't. You can prove a theorem that says, under certain condition, the phi will be the same no matter which unitarily invariant norm you choose. And we know what the answer is. When a certain reference measurement exists, then we know what the answer is. It's a special one. It's called a symmetric informationally complete measurement. And the condition is simply that if we look at the measurement operators, they have a constant overlap. If I take the trace of the product of any two, then I get exactly the same number. So another way of saying it is what the operators in the reference measurement correspond to is a set of d squared lines in a complex vector space, such that the angle between any two of them is the same. This is called a maximal set of equal angular lines. Now, when these things exist, then we know what the irreducible quantumness is, and we know what the Born rule looks like when written in terms of the irreducibly quantum reference measurement. It boils down to this, something that's worth staring at. But let me show you the mathematical troubles that QBism gets into if it tries to keep pushing this program. Here, I said it. It's been an open mathematical problem for 22 years. Do the seeks exist for general finite dimensions? It's been an amazingly fruitful question to ask from the point of view of mathematical physics, and has led to surely over 200 papers by now. But we don't know the answer still. The latest that I've seen comes from a slide courtesy of Marcus Grossel. These objects have been proven to exist in all dimensions less than or equal to 53, and in a smattering of other dimensions going all the way up to 5,799. There is good numerical evidence for them existing out to about 5,000 digits of accuracy in all dimensions to 193. But it's turned out to be an immensely hard mathematical problem. And the trouble is that despite its very simplicity in stating the question, it goes deep into number theory. Just like it was very simple to state Fermat's last theorem, but then it led you into number theory for 300 years. I have a little fear that that's going to happen here, but not so much of a fear. Mostly, I think what we found is something in quantum theory that's of a deeply number theoretic origin. And strangely enough, it has come about, not because you have to interpret quantum mechanics in epistemic terms, but if you do interpret quantum theory in epistemic terms, it has pushed the program of trying to rewrite the Born rule, and rewriting the Born rule in the simplest possible way from a normative stance has led to this deep mathematical question. So what will a QBist do with this expression? Well, first and foremost, think long and hard on what it indicates about quantum reality. What is the meaning of this deep symmetry? And I haven't revealed this yet, but fulfilling the seek condition appears to be related, or in fact is related, to Hilbert's still unsolved 12th problem. So there's a lot of deep number theory going on here. This would mean algebraic number theory plays a hidden role in quantum theory's normative suggestions. Now, it could be that that really doesn't tell us anything new about quantum theory, but my guess is when we find something new and genuinely distinct about quantum theory, it helps us in the project of understanding what quantum theory is about. Could the Everettians, the Bohmians, and the GRWians, and the time backwards people and the super deterministic people, they all seem to already know what quantum theory is all about? Could they really, without knowing such new and surprising structural features of it, ones that totally reshape the formalism away from the usual old debates? My opinion is pah. But QBism is a project, a project to be developed. And with that, I'll thank you for your attention.
Thanks so much. That was great, Chris. Thanks so much. We have several minutes right now. We're going to take a 5-minute break before the next talk. Jacques will give the next talk. So until then, we have some time for some quick follow-up questions. I've gotten a couple of questions in the chat. I'm going to go in order. If you'd like to ask a question out loud, please use the hand-raising tool in the participants window. I see a bunch of questions already there. I'll try to get to everybody. I'm going to prioritize people who haven't asked questions before. So I had a couple of questions in the chat from earlier on. In particular, let's see, the first question I have is from Mauricio. I actually had 2 quick questions in the chat from Mauricio. Do you want to quickly ask them both?
Actually, the second one is fine with me. What can scientists and physicists learn from doing Bayesian theory in general?
That's the question?
Yes.
What can scientists and physicists in general learn by using Bayesian theory?
Yes. I'm Mauricio from the mails, you know.
Sorry, let me just get you on my screen so I can.
Okay.
So I can see you.
I have sent you some mails on the last months.
Okay. I mean, what can you learn from learning calculus? You learn how to do things with a theory that you couldn't do otherwise. And Bayesian theory is an example of that. Now, there are practicing Bayesians, workaday Bayesians, who actually use it to solve problems. And then there are philosophical Bayesians who probably never solve a problem with Bayesian theory in their life, but they say this is the right way to think about probability theory. And if I think of it in this way, I won't get tripped up on various conceptual questions. So I have to admit of not being a practicing Bayesian. I wouldn't know how to do a calculation with it, hardly. But I will say that it, to us, has cleared up a number of conceptual questions and maybe has mostly played the role of cleaning out the underbrush in the interpretation problem. So many people want to say, and in fact, they're smiled upon mostly by the philosophy of physics community, if they have an interpretation of quantum states that's objective. If a quantum state is a state of reality, then you're a good guy. So you Bayesian, you Bohmians, you're a good guy. You Everettian, you've got real quantum states. You're a good guy, and so it goes down the list. The superdeterminists, who would have thought they'd be good guys? But they're good guys. They've taken away the whole freedom in our lives, but they've got their objective quantum states, so they're good guys. We have taken the tack that they're not objective, and in that way, we don't have the same problems. Among other things, if you push this point of view, I think you're only going to end up with one consistent interpretation. If you view quantum states ontically, well, there's the GRWians, the Bohmians, the Everettians, the backward in time people, there's 15, 20 interpretations. There's probably more than that. But so the point is, it clears out the underbrush and leads you ineluctably in a certain direction. And ultimately, then it says, the way we need to understand the structural features of quantum theory is from a normative point of view. And then I would say, oh, now we say, why these normative rules? That's going to tell us something about reality.
Thanks, Chris. With the question about what we've learned from Bayesian reasoning, I was worried that you were going to try to answer in the form of a Bayesian update, but it's good. So in order, I have next Nina, and then I have Saslav. Nina?
Thanks. My question was about something that you said at the very beginning. So you said that QBism is a methodology. Do you have that kind of simple?
You got to pronounce it right, or I won't answer you. It's QBism, like the art movement.
Okay, so you said that QBism is a methodology. So I'm just curious what you mean, if there's like a simple way of saying that. So I mean, I think in particular, listening to what immediately followed that, it seems like what's happening is your QBists are assuming that the quantum state falls on a spectrum, but it's a very limited spectrum in terms of what's there, and there are no ontic options there. It's all something to do with information or belief or something like that. And or maybe there's also a basic assumption about wanting to have probabilities be something very minimal in terms of what they are in the world. So what is the methodology is there some methodology that leads to those assumptions, or is the methodology make those assumptions and see what happens? Or yeah.
Oh, yeah, sure. So I think I answered you partially in my answer to Mauricio. So the idea was to start with the assumption, or I think Rob Speckens put it very nicely in one of his toy theory papers, where he said the idea not to back down on is that a quantum state should be understood in epistemic terms. So it was to take a gamble, take a Darwinian gamble, and say, I'm not going to waste my life on ontic interpretations of quantum states. Somebody else can waste their life following that route. If I waste my life, I'm going to have wasted it under the assumption that quantum states fall somewhere in the epistemic spectrum. And then the methodology has always been to check consistency constantly. So let me give an example of that. So once we had decided that quantum states were epistemic, what does that imply about measurement operators? Can measurement operators be ontic, but quantum states be epistemic? That's the kind of question that's explored. And ultimately, we convinced ourselves that if quantum states are going to be viewed epistemically, consistently epistemically, then measurement operators too have to be understood epistemically. And in fact, in the little rewrite of the Born rule that I showed you today, it shows you exactly how to do that. Measurement operators can be represented by conditional probabilities. And so therefore they're epistemic from our point of view. So the methodology was to start with a half-baked, half-worked-out epistemic conception of quantum states, force it to be consistent and see where that takes you. And then the idea was that at every step of the way, when you identify something as personalist, Bayesian, or subjective, then you know that that thing cannot correspond to an element of reality. So we went down a long list of things that cannot correspond to an element of reality. And actually, we're left with one thing that can correspond to an element of reality. And that is the Born rule itself. The Born rule is indicative of something about reality. So you ask a QBist, what is your element of reality? I'll say the Born rule. And then they tell me, if they say, well, tell me more, that's too thin of an answer. I say, okay, you got your quantum states. They're your element of reality. Tell me more. And I think that we're both stuck in the same sort of situation. We have a piece of the mathematics that corresponds to reality, and now you still have to go further in story making.
Nina, does that answer your question?
It does, thank you.
Okay, we may have time for two, possibly only one. I have Czaslaw, and then I have Gerardo. Czaslaw, go ahead.
Czaslaw always asks me questions. You should put him on the back burner.
Well, what do you think about that? Can I?
I'm fine, whatever Chris wants.
Okay, well then Gerardo, go ahead.
Oh, nice. Thank you. Thank you for the talk. It was very, very entertaining. Okay, so I think this is the type of questions that you will not like, okay? So I am a little bit confused about your response regarding modeling's claim. And my problem is this. As far as I understood, your response has to do with how to view correctly probabilities and with how this in one part, and the other part is with how to correctly understand quantum mechanics. And in your view, the Born's rule and probability plays the crucial role. And my problem is that you can state Bell's theorem, the theorem, without any reference to quantum mechanics. You have only two main assumptions, factorizability, and you have settings independence, or measurement independence,
Okay.
whatever, and you can derive the inequalities. So if that is the case, how your response can be on point?
So maybe in the discussion, we won't have time for it now, but in the hour-long
Yeah,
discussion,
we'll have to close up in less than a minute. So sorry.
I'll show you why I think that's just wrong. The setting of the Bell considerations has click, click, click on Alice's side, click, click, click on Bob's side, as if God could look down and see all the clicks happening. And both in the Everettian view and in the QBism view, you don't have that. In the Everettian view, from Alice's side, there are clicks on Alice's side, but not on Bob's. On Bob's point of view, there are clicks on Bob's side, but not on Alice's. And then, as David Wallace says very nicely in his book, when you take the view of the universal wave function, there are no clicks at all. Bell needs that extra stuff. He needs the consideration of both clicks, both sides of the story simultaneously. And QBism eschews that, and many worlds eschews that. And maybe even the relational point of view of Rovelli eschews it. So that's how we get around that. But I didn't answer your question about Maudlin, but since I got to shut up, I'll answer that one later.
Okay,
I want to thank everybody for your great questions. Thanks again, Chris, for the wonderful talk. And yeah, we will have time for the final hour for a much longer discussion period. We always have plenty of time. And I see lots of questions. I'll hang on to all of them. So just stay tuned. So for now, I want to thank Chris again. And everybody take a couple-minute break. We're going to actually start at a minute after the hour. So go take a break and we'll get set up for the next talk.